So again,
Sorry.
Right, this.
Yeah.
Yeah. So we've been turning like who is going to have the honor to introduce the speaker today. I'm introducing the speaker of today. So it's a pleasure to introduce Marco Zimmerling. So Marco is with us at the TU Dresden. So he is a research group leader here at TU Dresden. His group is called the Network Embedded Systems Lab, which is affiliated with cfaed, which we have been mentioning in this seminar series a couple of times. He's also associated with the Faculty of Computer Science. He works on embedded hardware and software solutions for dependable and sustainable wireless cyber-physical systems, which is a very good topic for the seminar series. He holds a PhD from the ETH Zurich, which is of course a very famous organization, and he did his diploma thesis at TU Dresden. So kind of he went to Zurich and came back to Dresden, and I think Dresden is very happy about that. Yeah, so it's a pleasure. I'm really looking forward to listening to your talk. So we actually work very close together, but we only get to speak when we are giving presentations in the frame of a Tunisian seminar. So it's kind of funny. Marco, please go ahead.
Now I should start to share the slides. So yeah, thanks for inviting me. It's really an honor to be part of this seminar series and to talk about some of the work that we have been doing together with colleagues from different places. So from now 4 different places. That includes one of my PhD students and PhD students at the Max Planck Institute in Tübingen, the Institute for Intelligent Systems, as well as the group of Lothar Thiele at ETH Zurich. Let me mention right away that I'm not a control expert. So in this effort here, Sebastian and Dominic, they had the control intelligence or experience, and we try to work together on what I'm going to show you. And yeah, so let's just start with this video, and I let you watch this video for 1 minute. Yeah, so I think some of you may now wonder what the hell is going on in this video. And that's essentially the roadmap of this talk, to explain to you some of so what's going on in this video, what are the different components in terms of hardware and software, how they are interconnected and working together to achieve the behavior that you just saw, and why is this actually relevant for real-world applications. We will then move on and talk about some fundamental challenges in realizing what you have just seen, and highlight on an overview level how we approached and solved this problem. So let me start with the components and their relevance for real-world applications. So this is a snapshot of the video, and as you can see on the left side, there are 2 inverted pendulums, and this is just another video that illustrates the operation of a single inverted pendulum that is being controlled by a local controller that's connected over wires. So you actually see the wires over here, and there's this card that moves along a track. It's driven by a DC motor, and it tries to stabilize this blue pole in the upright position. And one of the students, Dominic, he's actually introducing a disturbance to this physical system by touching the pole. But still, as you can see, the system, or the control system, is able to stabilize this pole in the upright position. As you can also see, this is an unstable equilibrium, so you need to constantly move the card in order to stabilize the pole in the upright position. So this is a schematic of this card pole system, and you may try it at home to stabilize maybe a pen or a wooden stick with your hand. And the problem gets harder the shorter the stick is, or the larger the weight of the weight at the tip. So some of these systems they allow you to attach a certain weight to the tip to make the problem more challenging. So what's going on here? So this card is equipped with angle sensors. So two types of sensors to sense certain properties of this physical system, of this card pole system. And we get two direct measurements. One is the pole angle. So this is actually indicated in the figure here. The angle between the upright position and the current position of the pole and the card position along the track. And based on consecutive readings of these sensors, we can also determine the angular velocity of the pole and the velocity of the card. And these four variables essentially describe the state of this physical system. So these are the state variables. And based on current state variables, there's a controller that computes controller signals, or in this case, a single control signal, which is the voltage that is applied to this DC motor at the card. So this voltage essentially means in what direction the motor is moving, left or right, and how fast it's moving. And this essentially closes the loop, and we arrive at what is called a closed loop control system, where we have the physical system, we have sensors that measure properties of the system, we have a controller that takes these sensor readings, computes control signals in order to force this physical system into a certain state. In this case, it tries to stabilize the pole. And for this talk, or just to give you a very informal definition of what closed loop stability means, is it essentially entails that the state of this physical system evolves in a well-behaved manner. So for example, there are different notions of closed loop stability, and they are actually very precise in terms of their mathematical foundation. So given a model of the entire system, one can prove formally whether the system is stable or not. And there are different notions, but as you can imagine, that it means that the state evolves in a well-behaved manner. For example, for a bounded input in terms of the control signals, the output, the state is also bounded. So that's one notion of closed loop stability. In our case, we of course don't want the pole angle to grow too large, so the pole falls over. So we are trying to stabilize the pole within plus minus 1 to 2 degrees from the upright position. So the state should be bounded. So that's the first component of this video. These are the physical systems with sensors and actuators on the left side. On the right side, you see a controller. So that's device number 18 in blue. And this is a small embedded device with a microcontroller that executes the controller. And using the network, we close essentially 2 feedback loops, one for each of the 2 pendulums. So sensor readings are being sent from the left side to the right side to the controller, and the controller computes control signals for both these pendulums and sends them back to nodes 1 and 2, which are attached to these pendulums. And then actuates the motors accordingly. And this is not a wired network. So these nodes are equipped with low power radio transceivers. So that's what is indicated here in green on the red side. You actually see the antenna of the low power radio. That allows to communicate using the wireless medium messages from A to B or between the controller and these 2 pendulums. And since this is a low power radio, we're trying to reduce the energy cost and consumption of these devices as much as possible, so they can be battery powered or actually harvesting energy from the environment. We need to get the energy footprint down as much as possible. And therefore, we are using low power radio transceivers. And these transceivers cannot transmit very far, only maybe indoors a few tens of meters. And therefore, the network in the middle is a 3-hop network. So as indicated here, for example, the control signals or the sensor readings between the upper pendulum and the controller may need to travel along 3 hops. So from node 2 to node 5, from 5 to 12, and from 12 to 18. So it takes 3 hops to get messages from the left side to the right side, or vice versa. So we have the wireless multi-hop network in the middle. And overall, this is what we call a wireless cyber-physical system. And these systems, as we just saw, rely on feedback control and coordination. So we're using sensors to understand what's going on in the physical world and communicate these sensor readings to controllers that may run on microcontrollers, as we just saw, or on edge devices inside the cloud. And then these controllers compute control signals that actuate something in order to force these physical processes into some state that is desirable for the application. And if we are able to close these feedback loops across wireless networks, this allows us to have much more flexible systems, flexible interconnections between these different components. It also allows us to scale up these systems much more effectively and cost efficiently. In particular, when we are relying on low-cost off-the-shelf hardware that just costs a few dollars per unit or even less. And this is really the underlying principle of feedback control and wireless CPS that is believed to be extremely useful to address some of the global challenges we are facing as a society, such as precision agriculture using drones, for example. So if you want to network or coordinate drones, you need to have a wireless network between these drones and close distributed feedback loops across this network. Also, you may want to install sensors and actuators in cities, optimize traffic flows, how energy is used in buildings. And if you want to retrofit these buildings, it's a major plus if you don't have to install any new wires in these buildings. You just use battery powered devices. And industry is, of course, a huge playground. And in particular, there's this vision of smart manufacturing. So if you look here on the left side, there's a picture of a traditional assembly line that is installed to produce the same product over and over again for many, many years. So it's a very rigid concept that has been used or is still in use today in many manufacturers around the world. And using this new CPS technology, we would like to turn these factories into smart factories, where we have different components and humans interacting with each other. Here on the right side, you see, for example, drones that are flying. We have robots on the ground. And these robots allow us, or this flexibility allows us to build factories that are much more flexible and scalable. So when a new order arrives at the factory, we can reconfigure the system to manufacture a new product or a product with a different property. And these robots can form groups, assembly lines on demand to achieve these very highly individualized products and still achieve very high quality. And that allows these factories in order to actually live longer. You don't have to reinstall the entire assembly line. If there's a new demand coming up, you can use the existing components, at least to a certain extent. And that, of course, allows you to react very quickly to changing market needs and to maximize your profit margins. So that's the overall vision of a smart manufacturing. If you have a deeper look inside such a smart factory, you may have different production cells, cell A, B, C here in this figure. And these cells reside on a factory floor. And there's an application layer that essentially controls the entire operation of such a smart factory. And if you look at the level of individual cells, as indicated here in this figure, you have human operators, we have supply chain entities that bring certain components to the places where they actually need it. We have robots on the ground driving around or flying around. We have remote sensors, light sensors, maybe air pollution sensors, video cameras. And many of these components should or have to be interconnected using a wireless network to achieve the desired flexibility. Whereas between cells, or when you look at the connection between to the application layer, of course, there are also wired networks, Ethernet cables that are being used for communication in these systems. So it's a hybrid wireless wired system. And let's have a closer look at this swarm here at the top, where we have some drones. And these drones, for example, are envisioned to be used to bring products from A to B, to actually construct certain things as a team, because maybe one drone is not strong enough to carry a certain element of what you're trying to build. So when you look at individual drones, then each drone needs to stabilize its flight locally. Right? So there's a control loop that runs at a pretty short update interval. So that's the time between consecutive sensing or actuation tasks. So of 10 milliseconds or even shorter, in order to stabilize the flight of each drone. Because there might be wind gusts or things going on, so you need to constantly measure how high you are above the ground, what's the tilt, and so on, and then you have to react and actuate the different motors in order to stabilize the flight. So there's a local control loop on each of these drones. In addition, if they want to act as a team, they also need to exchange state updates with each other using wireless communication in order to, for example, keep a desired formation or avoid collisions with one another as they are flying. And these state updates have to be exchanged with an update interval of 200, 100 milliseconds, or even faster, depending on the speed they are moving and the required control performance. So we have two kinds of levels here, right? So there's a local level, local control loops, and we have distributed control loops that are being closed over a wireless network. And you can, what is sort of nice about what I showed you in the beginning in this video with these inverted pendulums is that these inverted pendulums actually have physical dynamics that are very close to those of real mechanical systems, like these ground robots or flying drones. So in order to stabilize a pole locally, you need to cater for update intervals of tens of milliseconds. At most 40, 45 milliseconds is what we could realize with our inverted pendulums that we used in this testbed. And to mimic the coordination of multiple of these agents or robots or drones, one can pose the control task of trying to that these cards, the cards that are at the bottom of these inverted pendulums should move in concert. So they should move as closely as possible from left to right while they are trying to locally stabilize each pole. So we have very similar physical dynamics and control objectives when we use a set of inverted pendulums that are being coordinated over a wireless network. So that brings us back to one of the snapshots of this video, and would like to highlight here again that one of the key features that or objectives, if you want to do distributed control over a very dynamic system, such as a swarm of drones, you have to be able to do this despite very dynamic network situations. And this is what you can see in the video again. So I'm showing it again now because now I talked a lot about the different components, and maybe you can appreciate a bit more or understand a bit more what is going on. And in particular now, one of the students picks up the controller, this node number 18, and he walks around the testbed area, which leads to major changes in the network topology, how nodes are interconnected, how they can talk to each other. But still we see no difference in the control performance, because as you can see here, the pendulum is still being stabilized, as if the network was completely static. And you would see the same performance even if all nodes would be moving around, as it is indeed the case in a drone swarm or a robot swarm. So what are the fundamental challenges here? So why is this a challenging problem to solve? And let's zoom out again and look at a possible cyber-physical system where we have here distributed devices. In blue, we have sensors. In orange, we have actuators and a few controllers. There's one primary controller in dark gray and two backup controllers that are just there in case the primary controller fails. And what you need to do is to read out the sensors. You maybe want to do some filtering, some local pre-processing, and you have to buffer the sensor readings locally. So that's what's going on these blue devices. And then these sensor readings have to be communicated. So they have to be collected from these blue devices at the gray controllers using communication. Then the controllers compute control signals. Again, they are doing some kind of processing, some filtering, and again, they have to do some buffering of these messages that they have to send back to the actuators. Again, using the same network to multiple actuators, and they then do the actual actuation. So this is a pretty complex pipeline that is also distributed spatially, as you could see. And closed loop stability is an end-to-end property that is really related to the end-to-end properties along this entire chain. So from the beginning of the sensing through the local pre-processing, communication, control, computations, again, communication and buffering, until you actually start to actuate at the physical system. So you really have to look at the end-to-end along this entire path. So you have to look at all cyber-physical components in terms of hardware and software along this chain, and also consider the physical dynamics of the system you want to control. The communication network plays indeed a major role, and I want to focus a bit more on this in the following. So traditionally and still today, many feedback loops in cars and airplanes and industrial systems are based on wired communication systems, such as field buses, and more recently moving towards Ethernet-based solutions. So we have CAN buses and so on. And these buses are built with dependability and predictability in mind. So there's usually you have a global clock, and nodes that are connected to this bus know exactly when they are supposed to transmit something, when they are supposed to be quiet, and there's also redundancy built into these systems. So that makes control design much, much easier, as compared to this new setting that people would like to look at and enable, where we replace this wired network with a possibly low-cost and embedded wireless network, and use this network to close multiple feedback loops with possibly, as indicated here, multiple remote controllers that are trying to control multiple physical systems. And because this is a challenging task, prior work has not addressed a certain dimension here, as I'm going to explain. So when you look at existing work that has actually been validated or demonstrated in the real world, then we can look at two different dimensions. So one of them is the network diameter. So is this a single hop wireless network where every participant can directly communicate messages with every other participant? Or is this a multi-hop network where one needs to relay messages in order to reach the controller or the physical system? So that's on the x-axis, the network diameter, and on the y-axis, we have the process dynamics. So if we're looking at faster physical systems, like mechanical systems, like drones, or these kind of things, or inverted pendulums, where we have to cater for update intervals in the range of few tens, maybe hundreds of milliseconds, or we're looking at slow dynamics. So if you're doing control in a chemical plant, then most likely we're talking about seconds in terms of update intervals. And there have been, of course, a few practical works that try to do this in the real world. Here, for example, there's the work from KTH in Sweden, where they showed that it's possible to control two double tank systems using a very small single hop network. So this is a very small installation. So every of these nodes that you can see here can directly talk to each other. So there's a single hop network, and these water tank processes are pretty slow. So we have to communicate every couple of seconds. Then there have also been works on multi-hop control. For example, people in Trento, they installed sensor nodes along the road tunnel to control the light intensity of the lights at the top of the tunnel. So this is a very long network, so hundreds of meters. It's a very deep multi-hop network. But again, you don't have to be that super fast in order to adjust the lighting level to the incident light at the ends of the tunnel. So you can send updates every 30 seconds or minute and you'll be fine. However, if you want to stabilize a pole or inverted pendulum, as we saw in the beginning, you have to be pretty fast. So you have to do the sampling and actuation every few tens of milliseconds. And this has only been demonstrated for a single hop network. So essentially here on the right side, you see the network. It consists of only two nodes. So you have the controller node, and you have one other node attached to this card that's annotated with position node or angle node. Yes, I think they actually use two nodes, one to do the sensing and send the sensor readings to the controller, and then one that takes the control signals from the controller and applies it. So that's a single hop network. And there hasn't been anything here in this upper right corner, which is however needed if you want to do want to support the applications, some of the applications that I mentioned in the beginning, including smart factory, smart manufacturing scenarios. So why is this challenging? What's the problem here? And one of them, or pretty obvious problem, is that if you compare Ethernet with gigabits of bandwidth to a wireless network like Bluetooth Low Energy or Zigbee network, where you have a pretty limited bandwidth. So it's gigabits per second if you want to have a number compared to a few hundreds of kilobits per second, or maybe 1 or 2 megabits per second now with the new BLE, Bluetooth Low Energy standards. Moreover, we have longer delays, right? So these sensor readings have to travel across the network and then have to travel back. And that results in delays on the order of hundreds of milliseconds in the traditional systems, or possibly even seconds. Whereas in these more wired installations, it's nanoseconds or microsecond latencies that we're talking about. And you have unpredictable jitter versus negligible jitter in these more traditional wired control systems. And these longer delays and jitter are not only a result of the lower bandwidth that we have using these radio transceivers, it's also because of the way these the wireless communication protocols are operating. And I want to show you or illustrate next how I would say 99% of the wireless protocols operate. And what they do is they try to build a graph, or they try to construct end-to-end routing paths that allows the network to transport messages from the blue node on the left side using these intermediate nodes. So these nodes are relaying the messages forward towards the controller. And in order to construct such a path, these protocols need to understand the conditions or the properties of the network. And this is what we typically call the network state. So what is the current topology? What are the properties of the network? And based on this collected network state, they can try to construct these routing paths. So one of the first things nodes or these protocols need to do is they need to understand what are the neighbors of specific nodes in the network. So here we have this gray node, and it needs to understand what are my neighbors. And it finds out there are 6 green neighbors here is indicated. And this takes time and energy. So this node needs to exchange messages in order to understand that it has 6 neighbors. Then it also needs to understand what is the quality of the links between me and my neighboring nodes. So how good is the communication between my neighbors? And I might have very, very weak links to neighbors or very, very strong neighbors. And then I need to choose to which of these neighbors I would like to forward my messages. So if I have a message that I wish to send, or I have received a message that I have to forward, I need to pick one of these neighbors to forward messages to. And this node should, of course, lie in the direction of the destination. In this case, that's the gray controller on the right side. So it picks this node that has a good link and lies in the direction of the controller. And every node in the network needs to do this. And of course, there might also be contention scenarios where multiple nodes wish to send their messages to the same node. And there needs to be a mechanism to decide which node sends first, which node sends second. And eventually as you can see here, the protocol was able to construct a routing path between the blue sensor node and the gray controller. And also indicated here are the message queues. So messages that are being forwarded have to be stored locally before they can be forwarded, because maybe I have to wait until one of my neighbors has transmitted a message and so on and so forth. And this leads to different fitting levels of these message queues as indicated here. The key problem now is, or the key observation is that because these protocols operate based on the knowledge or based on the current network state, the end-to-end delay, for example, so the time it takes to send a message from the blue to the gray node is also a function of the network state. So it depends on the current network state. And the problem is that this network state changes essentially continuously in a wireless network. And in particular, if we're talking about mobile entities like drones that are flying around and so on. So some of the communication links that existed may actually disappear because the node moved. So now this blue node cannot forward messages anymore. Some of the links may also become unreliable due to other effects like interference in the environment. And the protocol needs to detect that there has been such a change in the network. It has to identify, again, the neighbors, the link qualities, in order to form a new routing path to still be able to deliver messages to the controller. And this process takes resources, it takes time, and it's also unreliable because by the time you have found a new path, again, there might be a change in the network, as you can see here. So one of the links again became unreliable, and you may continuously adapt the routing paths to the ever-changing network state. So that's one of the reasons why we have long and time-varying delays in these networks. Long delays and due to multi-hop forwarding, and because things are changing all the time and messages are being forwarded across different paths. Also, we have significant and correlated message losses, whereas in wired networks, we have practically no message loss at all. And this is, as you can see here, because you might have queue overflows in the network. So if you are not careful enough and you're overloading the network, then nodes are essentially running out of memory. Therefore, messages could be lost, or messages can be lost because they are lost during transmission. So the plot here on the left side shows the reception ratio across a low power wireless link. That's a typical measurement that we see in the real world. And you can see that it actually varies quite a lot over a pretty short time window. So at some point at 4 seconds, it's almost perfect, close to 100% reception ratio. So very good link. And just a few seconds later, it's really a low quality link, and you have to deal with these ever-changing situations. And finally, the final challenge is that in many wireless systems, you have constrained information structures or constrained communication patterns that make control more difficult. So many of these wireless protocols, they support only very specific communication patterns. Here on the left side is what is called a many-to-one communication pattern, where Essentially, the protocol only supports forwarding messages towards a single root node. So it could be like a routing tree, and you can only forward the messages to this specific node. This could be the controller. And then there are, again, a whole lot of other protocols that only support one-to-many communication, that would allow the controller, for example, to send messages or the control signals back to the actuators. And these protocols only support these specific patterns or communication patterns efficiently, but they are very inefficient when it comes to supporting all-to-all communication or many-to-many communication, which is certainly needed if you want to do distributed control like swarm coordination, right? Because every drone here in the swarm needs to be able to exchange its state with all other drones. Right? And this needs to be very efficient. It needs to be extremely fast in order to meet the requirement of 100 millisecond update interval. So these are the key challenges. Maybe there are more, but these are the ones that I picked for this talk. And let's now talk about how we can address those challenges. And maybe it's not fair to say that this is the traditional approach, but still today I would argue that many cyber-physical systems are being designed in the way that I'm going to explain it next. So it's basically an isolated design of the communication and the control side. So there's a control engineer and a communication engineer, and they don't actually talk to each other. They may not even know about each other because one of them designed the 5G network and the other one designed the controller that exploits the 5G network. And what is typically being advocated on the communication side is that they try to do the best possible. So if you look at the 5G literature, there's this abbreviation URLLC, ultra reliable low latency communication. And what that means is that the communication guys try to make the network as reliable as possible. Sometimes you read 5 nines reliability. That means that the network tries to guarantee that 99.99999% of all messages are being delivered successfully. And at the same time, this should be extremely fast. So lightning fast, ultra low latency communication below one milliseconds. And and then based on these goals that are sort of targeted without talking to the control side beforehand, the communication system is being designed and eventually built. And then the control engineer picks up his tasks and he needs to design, or he needs to come up with a system model and then design a controller based on the system model and then implement this controller. And what is usually being done that in order to do the modeling and to do the control design, he or she assumes a certain message loss distribution, because the control engineer knows, okay, it's a wireless network, so messages will be lost. And he or she assumes a certain message loss distribution in the easiest case, which makes the control design and the analysis simple, is to assume that messages will be lost, but they will be lost such that these losses are essentially independent across time and space. So it's essentially a Bernoulli distribution that is being assumed. And the control engineer also assumes a certain delay distribution. In the easiest case, this is like a fixed delay, or you have a certain bounded delay with a certain distribution. And then, the controller is being designed, and maybe you even have a proof of stability based on that model and that design. But in many cases, it actually turns out that there's a huge mismatch between the control system or the control design and the communication system. What that means is that the stability analysis that is being done based on this model and is essentially not valid for the reality that the entire system will see once it is deployed on the real communication system. Because losses are very often not independent over time, because you may have a very long tail distribution of your latency. So on average, you may be extremely fast, right? So extremely low latency, below 1 millisecond. But if you have tail latencies for a few messages that are I don't know, hundreds of milliseconds, then of course this works against a controller that has been designed based on a certain assumption about the delay distribution. Maybe it was assumed that the delay is bounded by 10 milliseconds or 5 milliseconds. Right. So this is the challenge, and therefore we are not the first to do this. It's much wiser to do a co-design of the control system and the communication system. And in our case, what we did is we tried to design the embedded hardware components in this cloud here, the low-cost embedded wireless network components in terms of hardware and software, in order to address these challenges as much as possible. Because we would like to sort of simplify the system model and the control design as much as possible, and therefore make it possible to actually analyze, do a formal end-to-end analysis that is also valid in the real world. So first step is to design these components to address the challenges as much as possible. And then we are looking at the key resulting properties in terms of message loss distribution, delay distribution, jitter, and so on. And the control design takes these properties into account in the system modeling and the control design. So let's look at the design of the embedded hardware components, and I can only give a very brief overview here how one can go about some of these challenges, and there are essentially three main ingredients. It's hardware, the hardware platform, the wireless communication protocol, and finally it's the glue code is essentially a global scheduling framework that puts all the different pieces together at runtime. So the first component is this hardware platform, and the key goal here is to use a predictable platform that allows us to give bounds on the execution time of certain message exchanges or on how long certain tasks take. And what we ended up using here is a dual processor platform, where an application processor here on the left side is only devoted to executing sensing, actuation, and control tasks, and the wireless protocol executes on a separate communication processor. So they cannot interfere with each other because they're executing and using different resources. But still they can exchange messages with one another. For example, sensor readings that have to be sent across the network, they have to be pre-processed by the application processor, and then communicated to the communication processor, which then sends these messages across the wireless network. And this message exchange happens across a predictable interconnect where we have formal bounds on the time it takes to write messages into this interconnect and out of this interconnect. And these bounds can be taken into account when doing an end-to-end delay analysis, for example. So the key insight in terms of platform is to try to avoid resource interference as much as possible in order to make this platform or the execution timing predictable. The second component is the wireless protocol, which should be predictable as well in terms of message losses and or message loss distribution, to be more precise. It should be reliable. So most of the messages should be delivered successfully, and it needs to be efficient as well. And the key insight here is that one should exploit interference. So one should take advantage of interference in order to achieve these goals. And I'm going to talk about this a bit more on the following slides. And finally, we need to co-schedule all the different tasks that are executing in the system. So here on the top, you see sensing, actuation, and control tasks that are being executed by these application processors on different platforms. And we have this communication task or the wireless protocol that is being executed. And in order to minimize the end-to-end delay and jitter in the system, one needs to co-schedule all these different tasks in the system using a suitable scheduling methodology. So yeah, you may wonder, okay, what's the deal with exploiting interference? This doesn't make any sense because yeah, what we learned in our communication courses, and is typically done by most of the wireless protocols, is that one should actually try to avoid interference you should avoid collisions between different messages, because this results in an unreliable system. So what most protocols do is that they use knowledge about the network state, for example, to schedule communications. And so you want to schedule first this node. So this node is allowed to transmit its message to the common receiver. Then in the next communication slot, the second node transmits, and so on and so forth. So this is a sequence of transmissions, and there's no interference. There are no packet collisions. The key problem with this is that in order to do this kind of scheduling, this receiver R, for example, needs to understand what are its neighbors. So it needs to have up-to-date and accurate knowledge about the network state. But as we saw earlier, that network state changes. This is an extreme scenario where all the different wireless communication nodes, these drones are moving around. So there the network state changes continuously. And it turns out that under practical conditions, these protocols are not able to keep up with these fast network changes in order to achieve an effective and reliable communication. And one of the solutions that has emerged over the past 10 years and came from ETH Zurich, where I did my PhD, is to try to exploit interference in order to design wireless protocols that operate independently of the network state, that don't need to worry about neighbors and individual link qualities, and essentially operate independent of the network state. And that means that nodes essentially transmit synchronously. It's called synchronous transmissions. So multiple nodes transmit without caring about neighbors and what's going on around them. They just transmit. And if you make sure that they transmit at about the same time, it is possible for this receiver R to actually receive or decode successfully at least one of the messages. That's the key insight. And leveraging this insight, we developed a protocol that we then used, and is actually being used in the video that I showed in the beginning, where, for example, the controller sends a control signal, and it does this by broadcasting the message. This message is being received by neighboring nodes in its communication range, so by these three light gray nodes. And the protocol makes sure that these nodes also transmit or retransmit the message at about the same time. So these transmissions overlap in time, space, and frequency, but still, due to certain properties of these radio transceivers, these other nodes here are able to receive the message and relay it further down the network. And as I pointed out already, this happens without any knowledge of the network state. These nodes only have to wake up, wait for a message to arrive. So a message is being received. They wait for this message. But once the message is there, they just retransmit the message as fast as possible. And they don't need to know anything about their neighbors and link qualities and so on. And this results in a very deterministic communication behavior. One can give tight bounds on the time it takes to relay the message across the network. And another nice property that I want to briefly touch upon is that this also leads to a decorrelation of the message losses. May sound a little bit abstract, but let's make this a bit more concrete here. So if there's this controller node that sends a message, then there are three nodes in its neighborhood that have the possibility to receive the message. That's called receiver diversity. So there are three different receivers that can actually receive the message. And then all these three nodes also relay the message further. So this node here on the right side has a chance to receive the packet from three different nodes across three different wireless links. And if one of these links doesn't work when the message is being transmitted, then this is not really bad, because there are two alternative links that can be used or might be successful at this time. And this is called sender diversity. And there's also a spatial component, because initially, for example, here, this node that is to the right of the green arrow has one chance to receive the message. And then at a later point in time here, it has a second chance to receive the message from a different set of nodes at a different moment in time. And due to all these diversities, these three different types of diversities, we showed empirically using experiments, but also more theoretically in this paper here, scientific reports, that this leads to a decorrelation effect. And it's actually safe to assume that message losses are independent over time. Approximately independent over time. So based on the design of the embedded system components, we can mitigate or actually get rid of some of these challenges. So the jitter, for example, can really be considered negligible given the physical dynamics we are talking about. End-to-end delay is being minimized. Message losses are approximately IID Bernoulli, and we can support arbitrary traffic patterns. And then based on these very nice properties and taking into account these key properties, one can actually do a very simple control design, very straightforward control design. I don't want to talk about this now in more detail, but state predictions, pole placement, zero order hold, these are all mechanisms that are very well studied and very well known, pretty standard in the control community. So you arrive at a pretty simple basic control design that is actually tractable. So we can analyze the system, and indeed the system or the model and the analysis is actually valid with respect to the real implementation. And so we have a theorem that allows us to basically check if the system is closed loop stable in the sense of mean square stability. So we have a formal proof of stability, which is also valid with respect to the real physical system. And to show this, we validated this using testbed experiments, a live demonstration at different occasions. Here you see a few pictures from the Cyber Physical Systems at Internet of Things Week last year. So yeah, we essentially now could address some of these challenges and come up with a solution in this upper right corner where nothing existed before. And if you want to know or read more and understand a bit more detailed what is going on here, you may, for example, have a look at this upcoming paper. In the paper, you also find links to the software and hardware components that we used, which are largely open source. And there's also a link to another video. So that concludes my presentation, where we started out with this video. We talked about the different components and their relevance for real-world applications, some of the challenges of wireless control, and I tried to convince you that one should take control and communication into account at the same time, do a co-design to achieve an effective wireless control system. Thanks again to my collaborators, and yeah, I'm happy to take any questions you may have. Thank you.
So thanks a lot, Marco, for the nice presentation. So yeah, as usual, there is some time for questions. As usual, we always get overwhelmed with the amount of questions that we get. Marco, maybe I'll start. Okay, and Sanjay will follow. So I know this work and I think it's very cool. So one thing that I think I've already asked in the past is that something, so you have to pay the price somewhere, right? So I imagine, right, you get this predictability, you get this nice properties. So I am assuming that you spend more energy, but somehow maybe you don't. Can you, because you are maybe just retransmitting too much, right? So whereas if you would have like a state of the network, you could compute some paths where you don't have to retransmit so much, and if you know that the link is very stable, you don't care about having this spatial what is it called, redundancy kind of, right? Diversity. So can you comment on that? Is it that the price that we pay for having this predictability is more energy consumption, or what?
Yeah. I think this is a common pattern in many different fields. If you look at multi-core architectures, they have a higher promise to deliver higher performance, but they are very often less predictable in terms of worst case execution times, for example. And that's exactly the same trade-off here. So to get to this predictability, we are paying a price, and in terms of performance and in terms of bandwidth, for example. So how many messages we can get through the network per time unit. So that's suboptimal using this flooding approach. There are new follow-up works that improve on this, but yes. There's a price, and of course, in terms of latency, you're completely right. So if you know the system very well, so if you have a static network, and you know that, for example, it's deployed on a glacier, or I don't know, somewhere with a very little disturbance, you have very slowly changing conditions, and then it makes a lot of sense to exploit this network state, and you can definitely be more energy efficient. But you may not have.
Is this? Yeah, and is this quantifiable in a sense? Is it possible to? Is there a like bounds of how much you're theoretically losing, and also like to which extent this is a sensible approach to follow in terms of sizes of the network, maybe speed of the nodes, maybe reliability of the nodes, and these kind of things?
That's a very good question, and I would like to have this formula exactly to answer questions like this, right? So what's the trade-off? We did some rough approximations and some simple models where you can see for example, the amount of energy the traditional protocols have to spend in order to understand what's going on in the network. So what's the energy spent to collect information about the network state? And what is pretty easy to show is that at a certain rate of change in the network, this energy very quickly exceeds the energy that we need for the actual communication. Right? I don't remember off the top of my head all these numbers, but there's a plot that I remember. So to answer that question, it's not so easy to quantify. One can do approximations and get a feeling for this, but to precisely answer this, it's difficult.
Yeah, but that sounds actually very cool, right? Because then if you know the dynamics and so on, so then there is kind of a threshold from which your approach is also going to be more energy efficient and while still being predictable. That's really cool.
Yes,
okay,
yes.
Thank you. So Sanjoy, yes.
So that was a very interesting talk, Marco. I think this work is really cool. It's certainly, very, very impressive in what you've been able to achieve. I was curious about how much of this, of the overall system behavior is dictated by the computation and how much by the communication. I'm particularly thinking of the fact that you are, in a sense, custom building your, your control platform so that you can get very predictable timing behavior. But I mean, commercial platforms today can be quite powerful. So in a sense, like if, depending upon the scale, upon the physical distances, I would assume that communication cost and multi-hop communication cost would, in a sense, swamp computation cost, or am I misreading things? I mean, these should be relatively straightforward control loops, right?
I'm not sure I'm really getting the question. So do you mean about the in terms of timing? So how much time is spent doing computations, or
as opposed to communication? Right. That's exactly what I meant, because these seem to be relatively straightforward control loops, which means they should be I mean, my motivation is this: that to some extent, the platforms on which you are implementing your controllers are, you're saying that they would be dual core. They would have one core dedicated to the control, one to communication. These are, in a sense, customized for your application. The moment you go to customized hardware, it becomes an issue, or, cost comes into play. And if it turns out that only a very small fraction of your overall time is on computation because the loops are simple, whereas most of the end-to-end delay, which is what determines your stability, your control performance, is driven by communication, that might be overkill in it. So I'm just curious to know if you have any estimate of the relative times in actual deployments, particularly when you talked about these glacier things that Lothar works on, because these are very distant, right? So
Sure. Okay, so let me split my answer in two parts. So first is that so these dual processor or platforms are actually available off the shelf right now. They have different interconnection principles between the communication and communication processor. Usually they are based on shared memory, and you know that has some disadvantages. So you don't have these nice bounds compared to a like dual port memory kind of architecture. The other thing is, so communication, yes. So if we look at, so if I recall some of the numbers, so I think sensing and the sensing tasks, they are on the order of a few milliseconds. I think we are of course doing maybe some oversampling and do some buffering and some filtering locally, and that takes up to 10 milliseconds roughly. Versus the actual communication per message is on the same order, right? So a single message transmission, so to flood this message, like you broadcast the message across this wireless bus, right, as we call it, that takes roughly 10 milliseconds depending on the message size and the size of the network. And that's on the same order as the computation. If you need to exchange multiple messages between, let's say 20 drones, right? That takes 20 times 10 milliseconds, so 200 milliseconds. Yeah.
Thank you.
Yes, so there's a question from Wasim Hadrich. Yeah.
Hello, Mr. Marco. First of all, thank you for the presentation.
Thank you.
I have a question about how do you deal with the collision that happens when multiple nodes are sending data asynchronously?
We don't actually deal with them. We just force them, or we let them happen, and that means that we are trying to So we are not actively synchronizing the transmissions because they are synchronized on the fly. So let me go to this slide. I have to go to one of the slides to explain this. So we don't do anything special. We use off-the-shelf BLE radios or Zigbee radios, and these radios have certain characteristics that allow the node to receive something useful, even though the message collided. Okay, so what I mean is that, okay, here during the first transmission, there's no collision happening, right? So one node transmits, 3 nodes receive the message. Now these 3 nodes transmit and collisions happen. What I mentioned is that we don't actively synchronize these transmissions is because they are implicitly synchronized by receiving the message. So these 3 receivers here, they just have their radio transceiver on, so they are able to receive a message. And as soon as they receive the message, they execute a known number of instructions in order to trigger the retransmission. And this means that they're very, very well aligned in time. So there's a very little time offset. Of course, we still have frequency offsets and phase offsets at the other receivers, but due to the way these low power wireless receivers work, they are still able to decode the message successfully in many situations. Maybe I can very briefly try to explain. So these are low power, low cost receivers. So these are really, really simple receivers compared to maybe a 5G base station, where you do MIMO processing, you have very sophisticated physical layers. Here, these radios are extremely simple. They are designed to be low power. That means they are not operating close to the Shannon capacity. So there's a huge gap between the actual bandwidth and the capacity of the system. And this headroom, this gap allows these systems to tolerate if some of the bits are not correctly received. So they can detect these bit errors, correct for them using some kind of coding. And these bit errors happen precisely because of these collisions, but due to this gap, they can correct these bit errors, and eventually the full message is correctly received in many, many cases. I hope that that answers the question.
Yes, thank you.
So I do have a question. Is there any correlation between the number or the maximum number of hops and the technology that you use for transmission, and of course the delay, estimated time for doing the control computation? Because I assume that the larger is the network, the more hops will messages take to move to, to reach the destination.
Yes, yes.
And this will influence the time to reach, of course, the destination, and the time to compute. You get the information from sensors, and you compute the control, you get the to the actuators.
Okay. You mean when you need to collect multiple sensor readings from different?
Even if it's just one. I mean, if we do the bigger feedback loop is 100 milliseconds, and we have kind of 1,000 hops.
Yes, yes, definitely. So there's a linear behavior that
So it's linear.
basically scales linearly with the number of hops so it's all linear in the message length, the number of bits, the hop depth or the network diameter, and number of hops. And yes, so that's all linear using this specific approach that I explained here. So yeah, if you have a very large network, you essentially need to live with longer update intervals. That's true. So it's at some point you may not be able to support the specific control task anymore because your network is too large.
Yeah.
That's true. And because of this scalability problem, we have looked into this during the past 1.5 years, and yeah, hopefully something will be published soon on this.
Maybe you can change the wireless technology that you use. For example, you go for longer range technologies, and that's it.
Yes, I mean LoRa and Sigfox and so, but you have longer ranges, but they have very low data rates. It's only tens of kilobits per second. But yes, you can definitely tune the system by looking at a different wireless technology. That's one thing, and you can also do something on the protocol level. Doing some network coding, for example, you can get more messages through the network in the same amount of time. Or what you can also do, you can leverage event-triggered or event-based control concepts. So where the idea is that you only want to communicate when it's actually needed, versus doing strict periodic control. So and if you have some way of predicting the need for communication, you can actually spare many of these messages, and therefore you can scale up the system. You can support shorter update intervals, or many more agents, or more sensors, larger networks. Yes.
And we go to it becomes kind of an optimization problem to solve.
Yes. But the key insight from our work is that you really get much higher gains by letting control and communication talk to each other. So if you really try to co-design the system rather than in isolation, you actually see all these benefits.
Thank you.
You're welcome.
Okay, so if there are no further questions, so yeah, let's thank Marco again. So I'm just gonna use this emojis.
Thank you.
Thanks for the talk. And I think this was the last talk from the seminar series. Is that right?
Yeah, this is the last one.
So that was a good closing. So I hope this was beneficial for the students, especially in Tunisia. And yeah, let's see if we can repeat this next year.
Yeah. So thank you very much. Thank you all for attending, and thank you, Geronimo, for supporting these actions and the seminar instead of the workshop. And hopefully, we will get another one next year, locally in person, if COVID allows. So,
yeah.
Thank you all very much.
Cool. So then, everybody have a nice day, nice rest of 2020. Bye bye.
Bye.
Bye. Bye bye.